Okay, if you turn to the top of page 3, what we have here is a heating curve. A heating curve is a graph of temperature versus time. And what you're doing is you're starting out with a solid and you're heating it consistently, and that solid as a result is undergoing changes in temperature, then changes in phase, and you're ending up with a gas in the end. All right, in this case here, we happen to have the heating curve of water, because you'll notice that these two temperatures of 100 degrees Celsius for boiling point and 0 degrees Celsius for melting point would tell you that. So this here is the melting point of water, the normal melting point, I should say, of ice, to be specific. This here is the normal boiling point of water. Normal here has to do with the atmospheric pressure. We'll talk about that on the next page. All right, so that tells us this is the heating curve of water. But all substances have heating curves that look like this, in which you have 3 inclined portions and 2 flat zones. So picture this. Start with a block of ice or an ice cube straight out of your freezer at negative 20 degrees Celsius. And place that ice cube on your tongue. I'm sure you've had this experience where the ice cube freezes your saliva, and so it sticks to your tongue. If you don't panic, instantly you'll see within seconds that that ice cube begins to melt. And what's happening within those seconds is the temperature of that ice, at least the outside surface of that ice cube, is reaching 0 degrees Celsius. But any ice that's melting has to be at 0 degrees Celsius. Then the entire time that that ice cube is melting, its temperature, that solid liquid mixture, while it's melting, its temperature doesn't change. So melting is a flat zone here. Melting is a phase change. The reason why the temperature is not changing is because the particles aren't moving any faster while that solid turns into a liquid. The particles are spreading out. So we say that melting, being a phase change, is a change in potential energy. And that's why during a phase change, there is no change in temperature. Because during a phase change, we have a change in position of particles, a change in potential energy, not a change in speed or motion of particles, would be a change in kinetic energy. So it's either one or the other. And then what happens, after that ice is melted completely, and we have liquid at 0 degrees Celsius, then that liquid will steadily rise in temperature until it reaches the boiling point of the liquid. And the entire time that that water is boiling, turning from water to steam, again, there is no change in temperature. So both melting and boiling are phase changes, which are changes in potential energy, not kinetic energy. And after all that water has boiled and formed steam, then that steam can get hotter and hotter depending upon its surroundings. And at some point it can decompose. So going in this direction, we're calling that the endothermic direction, because as a solid turns into a liquid and then turns into a gas, energy is absorbed. Endothermic means that, the absorption of energy by that substance from its surroundings. Also in this direction, since the particles are separating, we say potential energy increases. An easy way to remember which segments of the curve deal with kinetic and which with potential is you could say the inclined portions are kinetic energy changes. Just like the letter K has an incline. And the flat portions, that would be these two plateaus here, would be potential energy changes. The letter P has a flat portion to it. So kinetic, 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 and flat portion's potential. Now, this might help you to remember what's going on with the particles so you can distinguish particles separating position versus changing in speed. So let's do a little human video. Let's say my hands represent, in this case, the molecules in a block of ice at -20. As we go from -20 to 0, what happens is the particles start to move faster. And then at 0, they move further apart. And then the water that forms, as it gets heated, moves faster and faster and faster. And then at the boiling point, they move further apart. So again, from -20 to 0, faster, 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 further apart. Then faster, 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 and then further apart. Seems silly, but I'm sure you remember that. Okay, now in the opposite direction, we have a cooling curve. The cooling curve would be energy released. So let's draw a cooling curve right here on the right to help you remember that. So, in the cooling curve, we start out with a gas. Then the gas turns to liquid. And it's all liquid. The liquid cools, the liquid turns to a solid. And finally, we have a solid. You might want to note, if we're talking about water, the temperature at which the liquid turns to a solid, which is freezing, is exactly the same temperature at which the ice melts, which is 0 degrees Celsius. That's why I note here that the normal melting point is also the normal freezing point in the opposite direction. And the opposite of the boiling point would be the condensation point, but that's never asked. All right, let's label this as condensing. So the cooling curve is exothermic, because energy is being released by the substance to its surroundings. Okay, let's continue with this page. Let's start doing some problems, some Q problems. You're going to need a calculator. And if you turn to the back, table T, you'll see that there are 3 Q formulas that pertain to quantity of heat. Calculating quantity of heat. So let's do that together now. Lower half of this page. Okay. How do we decide which Q formula pertains to the problem we have at hand? Well, there's only one formula that has a change in temperature. That's what that delta T stands for. So problems in which there's a change in temperature, we use that formula. If there's no change in temperature, then you have to decide, is it a heat of fusion problem or a heat of vaporization problem? All right. See if you recall, if you look it up in table B, that's where these constants are. Why don't you look that up right now? C is 4.18 joules per gram degrees Celsius. That's for water. And most of the time, these problems deal with water. Again, M is mass, Q is quantity of heat, delta T, change in temperature. And Q equals MHF, again, Q and M are the same. Quantity of heat, mass. HF is the heat of fusion. So while you're there in table B, why don't you make a note of that, which is 334 joules per gram degrees Celsius. Heat of fusion is the amount of heat energy needed to melt 1 gram of a substance at its melting point. So each gram of ice at 0 degrees Celsius requires 334 joules. And then, while you're there, also note the heat of vaporization, which is 2,260 joules per gram. Heat of vaporization is the amount of heat needed to boil 1 gram of a liquid at its boiling point. And the heat of vaporization from water is that value. Okay, let's do a problem. How many joules are needed to raise the temperature of 30 grams of water from 50 degrees Celsius to 70 degrees Celsius. So right away you see we have a change in temperature in this problem. 50 degrees Celsius would be your T1, your first temperature. 70, your T2. 30 grams, as you can tell from the unit, grams is for mass. And how many joules? Well, that would be your Q, which is unknown. So our formula is Q equals M times C times delta T. And in this case, the Q is the unknown, so let's solve for it. It would be 30.0 times 4.18 times, in this case, T2, 70 degrees, minus T1, 50 degrees. It's always T2 minus T1, which means you can get negatives here. And if you got a negative, that would be a drop in temperature, and that would be heat released by the substance instead of absorbed. So 70 minus 50 is 20.0. Since there's one decimal place, I'll write that in. And so your final answer has to be 30.0 times 4.18 times 20.0. You'll get here a Q of 2,508 joules. Now, if you were asked to convert this to kilojoules in a separate problem, you want to remember, again, 1,000 joules is a kilojoule. So you're going to have to divide by 1,000 in this case to go from joules to kilojoules, which simply means moving the decimal 3 places to the left. So that becomes then 2.508 kilojoules. Problem number 2. How many grams of ice can be melted by the absorption of 8,350 joules at 0 degrees Celsius? Notice they only give us one temperature here, because during melting, if you recall, as we said in the heating curve, there's no change in temperature. So that's a key, melting. So you know it's going to be heat of fusion. The 8,350, those are your joules, the Q. Now how many grams? That's your unknown, the M. So Q equals M times HF. Q, 8,350, equals M, which is your unknown, forgive me, times HF, 334. So to isolate M, since they're married by multiplication, you're going to have to divide the 8,350 by 334. So M is 8,350 divided by 334. You'll get from this 25.0 grams. So always include the unit in your final answer. By the way, if this were a problem that involved freezing, you would still use the heat of fusion. Except in the case of freezing, the energy is being released to the surroundings instead of absorbed by the substance. Okay, and finally, let's do a problem that involves the heat of vaporization. How much heat is needed to boil 100 grams of water at 100 degrees Celsius? Again, to boil, that's telling us to use the heat of vaporization. Otherwise, it would be to condense, but we'd use the same formula, the same constant, except that in the case of condensing, it's energy released. How much heat? That's your Q, the quantity of heat. 100 grams is your mass, and again, notice it's at 100 degrees Celsius because the entire time that the liquid is boiling, its temperature isn't changing, so we don't factor temperature into this formula. Q equals M times HV. The M is 100, and the HV is 2260, and our final answer 226 and 3 zeros joules. Okay, so you're bound to get one of these problems on the Regents, on a part 2, and typically what they ask you to do, if not to solve it completely, they'll ask for the correct mathematical setup. Notice when I plugged in the numbers, I copied them exactly as given in the problem. All right, I even put in the point there, and we'll talk about that later when we speak about significant figures. For now, you're doing pretty good. So we're at the end of page 3. You have 2 more pages to go with this unit. This is the longest unit, so bear with it, and you'll be fine.